Tonight, an interstellar visitor did the one thing a comet should not. Near the Sun, 3I Atlas flared hard and turned bluer than the Sun itself. Not a rumor, multiple spacecraft saw it. The brightness surged with a slope that normal models do not allow. Astronomers are checking calibrations, and the numbers still look wild. If it holds, we have a physics problem in daylight. If it fails, we learn how our eyes fooled us. Either way, the next weeks decide the story. Join the investigation, tap like, subscribe, and stay with us to the end. Start with the clock. October 29, 2025 perihelion day for 3I Atlas, the third confirmed wanderer from interstellar space to thread our inner solar system. From Earth, the object was swallowed by sunlight, hidden in solar conjunction. From orbit, a different story. Spacecraft that stare at the sun for a living block the blinding disk and watch the faint world just beyond. What they recorded is either the most dramatic comet behavior in years or the cleanest lesson in how hard it is to measure anything that close to the Sunday. Now the paradox. Ordinary comets brighten as they fall inward, steady, understandable, like a dimmer knob turned up. 3I Atlas did something closer to a light switch. Analyses of the spacecraft images say the brightness tracked distance with a power near -7.5, far steeper than the gentle 3 to 5 that textbooks whisper about. In plain words, as the object halved its distance to the sun, the light did not merely rise, it rocketed. Normal physics can chase that curve, yet it breathes hard while it runs. Color deepens the mystery. The measured light skewed towards short wavelengths, a hue that reads as bluer than the sun itself. That is a sentence you rarely hear without a raised eyebrow. Dust that only reflects sunlight usually copies the sun's color. Blue asks for either very small grains that scatter short wavelengths more efficiently, or gas molecules singing at specific lines, or plasma processes that dump energy straight into visible emission. Each path is possible. None is easy at this intensity. And the instruments did not agree once they agreed again and again. This is where good skepticism walks in. The Solar Terrestrial Relations Observatory, the Solar and Heliospheric Observatory, and a geostationary weather satellite with a space weather eye all have quirks. Stray light sneaks in, detectors saturate, backgrounds shift, cosmic rays stab pixels. Teams live in those details. They know that a lovely anomaly is often just a dirty window. Yet time sequences that evolve smoothly, color ratios that stay coherent as the object moves across the frame, and corroboration across different optical designs make a conspiracy of errors harder to stage. So we keep two thoughts in our head at once. Extraordinary claims demand extraordinary evidence, and we are collecting it. Extraordinary. Dismissals demand real alternatives, and we are testing those too. Between those poles sits the part that matters to you. Over the next episodes, we will pull apart what the cameras saw, translate the math into a story your intuition can feel, and stack the natural explanations from simplest to strangest. We will also pin down exactly which observations in December can end this argument quickly, without heroics or hand-waving. Here is the simple map of the territory. If gas emission dominates, spectroscopy will show it with lines that shout cyanogen, diatomic carbon, carbon monoxide, and carbon dioxide. If tiny dust dominates, polarization of scattered light will give that away. If emission outshines reflection while the object's path stays almost purely gravitational, that favors radiant processes without heavy mass loss. If the signal dissolves under calibration, we will tell you how and why, and the myth will die with the dignity of a careful post-mortem rather than a scandal. None of this turns the story into a cliff without a bridge. On December 19, the geometry improves and Earth's best instruments take another look. We have 5 weeks of patience to practice, and 5 weeks of preparation to do. That is a gift time to define decisive tests, to line up telescopes, to write down predictions before hindsight edits them. You're not just watching this, you are in the room while the decision tree is built, branch by branch. So when the new data lands, you will already know what each possible answer means. Keep your curiosity sharp and your standards higher. Wonder without discipline is hype, and discipline without wonder is a sleepwalk. 3I Atlas just woke us up. If you tried to chase 3I Atlas from your backyard on perihelion day, you saw nothing but glare. The object was in solar conjunction from our vantage point. It sat almost on top of the sun, drowned by daylight. The atmosphere scattered sunlight across the sky, the ground shimmered, and even the best terrestrial telescope was basically staring into a floodlight. Yet in orbit, a different story unfolded. Spacecraft designed to stare at the sun without blinking used a clever trick to look past the blinding disk and into the dim halo where faint things hide. The trick is called a coronagraph. Imagine holding up your hand to block a street lamp so you can spot a firefly hovering nearby. A coronagraph does the same with precision. It uses an occulting mask to cover the sun's bright face and optical baffles to strangle stray light, revealing the solar corona and anything passing through that field. Where the eye from Earth is overwhelmed, the eye in space is shaded, disciplined, and quiet. That quiet lets faint comets and tails speak. Different spacecraft bring different angles and strengths. The Solar Terrestrial Relations Observatory rides a path that gives it a side view relative to Earth, a helpful offset that changes the geometry of what is hidden and what is not. The Solar and Heliospheric Observatory sits near the Sun-Earth L, one balance point, gazing steadily with the large angle and spectrometric coronagraph. Camera C3, a veteran instrument with decades of calibration history. A geostationary operational environmental satellite built for weather and space weather carries a coronagraph channel that captures rapid sequences with low noise. None of these platforms was hunting 3I Atlas as a primary target. They were watching the Sunday. The comet wandered through their field at exactly the right time. Geometry matters. From Earth, the line of sight put the object inside the sun's glare cone a no-go for ground optics. From those spacecraft, the object sat just far enough from the masked disk to be imaged cleanly. Parallax did us a favor. A few degrees of separation in orbit translated into a clean view past the occulting edge. Add cadence and you get motion. These instruments collect frames over hours and days, so a faint smudge that shifts between images stands out against the structured but largely stationary corona. Why not simply wait for twilight and try from the ground anyway? Because daylight sky brightness near the sun is not a minor annoyance. It is a wall. Scattered light in the atmosphere is orders of magnitude brighter than the signal from a small, fast object at that distance. Even if you could point safely, and you should never attempt to view near the sun without certified filtration, the signal would drown. Space removes the atmosphere from the equation. Coronagraphs remove the sun's face from the frame. The combination makes the impossible merely difficult. There is also the matter of color and confidence. Instruments that work in space weather need stable, predictable performance across filters because engineers rely on those ratios to diagnose eruptions and shocks in the corona. When a transient object sweeps through and shows a color balance that tilts toward blue, it is not just a pretty picture. It is a measured ratio of short to long wavelengths, taken through known optics, corrected by well-worn pipelines. If one platform recorded a blue skew, you would worry about a local quirk. When several did, from different vantage points and optical designs, the worry shifts to the sky. What is the object doing? So a story that could not be told from a mountaintop became plain in orbit. An interstellar traveler slipped behind the sun from our viewpoint, and our machines, built to calm the sun's roar, revealed the whisper. That is why these near-sun monitors are quiet heroes. They turn noon into twilight. They turn glare into geometry. And on that day in late October, they turned a rumor into a record, giving us the data that fuels every question we ask next. Begin with the simplest picture. As a comet drops toward the sun, the extra heat liberates gas and dust. More reflective area means more light returned to us. Plot brightness against distance and you usually get a gentle slope, a few whole numbers in magnitude when the distance halves, a curve that patient physics can explain. 3I Atlas did not trace that curve. Analyses of the spacecraft images say its light rose with distance raised to about -7.5. That exponent is not a dimmer, it is a surge. Translate the math into something your hands can feel. Imagine hiking down a steady hill that grows a little steeper as you descend. That is ordinary comet behavior between -3 and -5. Now imagine that near the valley floor the trail tilts into a cliff. You do not stroll anymore, you scramble. That cliff is what the numbers describe for 3I Atlas near perihelion. When the sun-comet distance was cut in half, the light did not drift up by a comfortable factor. It leapt by roughly 2 orders of magnitude. The speedometer analogy lands the same point. 50 to 60 is a nudge. 50 to 5, 100 is not a nudge. Where did that exponent come from? Teams stitched together a timeline. Before the object sank into the sun's glare, ground-based telescopes measured a baseline that looked familiar. As the geometry turned against Earth, the space-based coronagraphs took over, building frame-by-frame records through closest approach. Put all those points on logarithmic axes and fit a line through the perihelion segment, then the slope reveals itself. The best estimate lands near -7.5 with uncertainty close to 1. Even the shallow edge of that range remains far from ordinary. You might ask whether a brief outburst could fake such a slope. A violent fragmentation or a jet that turns on for a few hours can spike brightness, then fade. The sequences here do show changes over hours and days, but the steepness persisted across multiple instruments and multiple frames. Outbursts are firecrackers. This looked more like a sustained burn timed to the closest approach. The pivot is that the curve steepened abruptly as perihelion approached, as though a threshold was crossed and a new regime switched on. To trust a curve, you have to trust the yardsticks. Brightness extracted from coronagraph images is not a raw pixel count. Teams subtract the bright, structured solar corona, remove instrumental backgrounds, and check for pixel saturation or nonlinear response. They map the object's motion to ensure they are measuring the same thing from frame to frame, rather than a wandering speck in a restless background. They compare photometry across filters, because a curve that exists only in one color channel smells like a calibration quirk. The result that matters survived those ordinary tests, then matched between platforms that do not share optics or detectors. What physical picture can create such a steep response? One option is pressure-cooked volatiles beneath a crust that cracked near closest approach, dumping fresh gas into space at rates far beyond what water ice can deliver. Another option is fragmentation that multiplied surface area in an instant, presenting the sun with many more faces to heat. A third is that reflected light was no longer the main driver, and that visible emission from excited gas began to carry the signal, which can raise brightness without the same geometric penalty that dust scattering suffers. Each option leaves fingerprints that we can look for in December. The exponent is not everything. You can pad a poor curve with fine words, so we add cross-checks. If reflection dominated, the coma should grow in step with the light, because more dust means a larger glowing envelope. If emission dominated, the surface brightness can climb faster than size. Early reads from the spacecraft suggest a vast envelope with brightness too high for dust alone, a hint that pushes the argument toward emission. That does not decide the case. It does say where to aim the next tests. Think too about force. If the light surge came from massive, one-sided outgassing, the nucleus should feel a tiny rocket push that telescopes can detect as an orbital residual, a position that drifts from pure gravity by just enough to measure. Reports so far suggest only subtle deviations. That is either symmetric mass loss that cancels its own thrust, or a process that shines without shedding much mass. Both paths keep the exponent dramatic while muting the shove, so the curve stands like a cliff at the end of a long slope. Natural mechanisms can, in principle, carve that cliff, but they require fine timing or unusual composition or both. Instrumental quirks can mimic drama, but they must conspire across platforms and persist through checks designed to break illusions quickly. The honest place to stand is on the ridge between those valleys, eyes on the December trail. The next measurements will not debate exponents on paper. They will ask the sky directly what substance made that light climb so fast and why it waited until the last possible moment to do it. Color is not a mood, it is a measurement. When observers say 3i Atlas looked bluer than the sun, they mean the light carried more short wavelengths than you would expect if it was simply reflecting sunlight off grey dust. Instruments do this by taking images through different filters. One filter favours blue light, another favours red. Divide the blue by the red and you get a ratio. Do the same for the sun in those exact filters. Compare the two ratios. If the comet's ratio is higher, the object is bluer than the solar spectrum. Ratios are quiet heroes. Absolute brightness is touchy, sensors drift, backgrounds change. Scattered light from the corona breathes in and out. But a color ratio divides away many of those troubles because the same optical path and the same detector quirks affect both filters. You are left with a cleaner signal anchored in how the spectrum is shaped, not how bright the scene is in an absolute sense. That is why repeat measurements of a blue tilt across different platforms carry weight. The details of calibration differ. The ratio keeps pointing the same way. Now, What physics can paint a comet blue? Start with tiny dust. When particles are much smaller than the wavelength of light, they scatter short wavelengths more efficiently. That is Rayleigh-style scattering, the same effect that makes our sky blue. If 3I Atlas lofted a cloud rich in submicron grains near perihelion, the scattered light could shift toward blue. There is a catch. Comet dust often skews larger, which tends to redden reflected sunlight rather than blue it. To lean blue by this much, you need a lot of very small grains and a way to keep them supplied and illuminated. Gas emission is the second door. Some molecules glow with characteristic bands when sunlight pumps them. Cyanogen tends to light up in the violet. Diatomic carbon paints a green band that often bleeds toward blue. Oxygen can contribute near 500 nanometers. If the coma is dense and energized, these emissions can dominate the visible signal. In that case, you are not seeing sunlight bounced off dust. You are seeing molecules radiate their own light, line by line, band by band. That flips the logic of color. You do not need exotic dust to skew blue. You need plenty of the right gas in the right radiation bath. The near-sun environment adds a third path. Plasma processes can push electrons into atoms and molecules with enough punch that they radiate in specific colors on the way back down. Electron impact excitation and related effects thrive where the solar wind is fierce and the ultraviolet field is harsh. If 3I Atlas carried a wide halo of neutral gas, the solar wind could carve it into a glowing sheath. That would look like extended blue-green emission spread across a large volume, not a tiny neon sign near the core. Reflection versus emission is the fork in the road. Reflection is sunlight borrowed and returned. Its spectrum wants to mimic the sun with only gentle tilts from dust properties. Emission is light created at the scene. Its spectrum bears the fingerprints of whatever atoms and molecules are doing the radiating. The luminous envelope reported around 3I Atlas, hundreds of thousands of kilometers across, matters here. If reflection ruled, you would expect the surface brightness to fall as the envelope swells, because the same light is smeared over a larger canvas. Strong emission can hold brightness across distance, because fresh energy is poured into the glow at every point. Could instruments fake a blue comet? Vignetting can make the center of a field more sensitive than the edge, and the shape of that sensitivity can differ by filter. Stray light can spill through optics in ways that slightly favor one color. Background subtraction can lean too hard on one band. These are real traps, and mission teams know them well. Yet a moving target offers a test. If the color tilt rides with the object as it crosses the field, if it appears in multiple filters with the same sign, and if another spacecraft with different optics sees the same tilt, the odds of a shared illusion drop sharply. What would clinch the case? Spectroscopy in December can separate bands into lines and confirm which molecules, if any, are shouting. Polarization measurements can test for tiny dust, because scattered light is polarized in ways emitted light is not. Spatial maps of color can show whether the blue is strongest near jets, across the whole coma, or in a shell where the solar wind ought to be slamming into gas. Each map narrows the options. Together they can tell us whether the blue is a dust story, a molecule story, or a plasma story. So when you hear bluer than the sun, do not file it under poetry, file it under physics. It is a ratio that survived rough conditions, a clue that points away from simple reflection, and a signpost for what to look for. Next, if the color holds under the better geometry of mid-December, it will not just be a headline, it will be a diagnosis. Start with the cast. The Solar Terrestrial Relations Observatory. A is a pathfinder that watches the sun from a vantage slightly askew from Earth, giving a side angle on anything that skirts the solar limb. The Solar and Heliospheric Observatory lives near the gravitational balance point between Sun and Earth and carries the Large Angle and Spectrometric Coronagraph, Camera C3, a workhorse that has stared at the corona since the 1990s. A geostationary operational environmental satellite circles above one slice of Earth and, among its weather duties, runs a coronagraph channel that fires off rapid, low-noise sequences aimed at space weather. Different orbits, different optics, one overlapping patch of sky during perihelion. Each platform brings its own way of seeing. The observatory at the balance point offers a steady stare with a wide field and a deep archive of how its images breathe from minute to minute. The Pathfinder's offset changes solar geometry so objects that are swallowed by glare from Earth's point of view slide into view from the side. The geostationary sentinel trades some depth for speed, capturing frame after frame with a cadence that makes sudden changes hard to miss and easy to verify. None of the three was pointed at 3i Atlas out of obsession. They were doing their day jobs when the visitor slipped through. What did they record? A faint source that marched along a path set by gravity, then swelled and sharpened in brightness as perihelion approached. The wide-field instrument caught the long arc and the slow climb. The closer-in cameras watched the envelope of light expand, and the hue lean towards short wavelengths. Most crucial, the apparent color skew and the steep brightness slope did not belong to only one instrument or one filter set. They emerged within uncertainties across all three. The story did not depend on any single lens or detector to be true. Cadence matters. You learn to distrust an isolated frame that screams miracle. The veteran coronagraph tends to report fewer images per hour, but with baked instability from decades of calibration. The Pathfinder ties together broad structures through time. The geostationary eye stitches a movie with high temporal resolution. When a target brightens, fades, and brightens again, in patterns that correlate between platforms, chance, and artifact begin to run out of room. When a blue tilt of the color ratio follows the moving source as it crosses a field and shows up again under a different optical design, the case hardens further. Backgrounds are the enemy near the Sunday. The corona is not a blank canvas. It is a living texture full of streamers and waves that change slowly and sometimes quickly. Teams build background models from rolling stacks of images, subtract the common structure, and then measure what remains that moves like a compact object. Each mission does this with its own software traditions. Agreement across those traditions is the quiet part of the story. It suggests that no single subtraction trick painted a comet where none existed. Geometry completes the triangle. The Pathfinder's offset from Earth provided a parallax that shifted the apparent position of 3i Atlas by enough to disambiguate it from coronal features that stay fixed relative to the Sunday. The Balance Point Observatory added the long view from the centerline, locking the position against a deep catalogue of past behavior. The geostationary eye compared consecutive frames so quickly that transient pixel hits from energetic particles could be tossed out by their one-frame flash. Align those three, and an interloper stands out as a coherent traveler rather than a flicker in the noise. No instrument is perfect. The veteran coronagraph carries scars on its detectors and known ghosts in certain orientations. The Pathfinder sees subtle pointing drifts as it maneuvers and bakes in deep space. The geostationary platform looks through the neighborhood of Earth, where scattered light paths can be complicated by reflections. These are not secrets. They are line items in calibration manuals and in the heads of engineers who have babysat these optics for years. The point is not that quirks do not exist. The point is that the quirks are different. When three different families of quirks all have to lean in the same direction to fake the same blue ratio and the same cliff-like brightness slope at the same time, the odds tilt towards signal rather than error. There is an elegance to how the pieces interlock. The slow and steady observer says the baseline is real. The side-angle scout says the geometry checks out. The sprinter says the timing and the evolution survive high-cadence scrutiny. Put them together, and you get a portrait that is more trustworthy than any single snapshot. But the disagreements help. Where one instrument underestimates brightness because of mild saturation, another with shorter exposures catches the peak. Where one filter set is noisy, a neighbor wavelength fills the gap. The overlaps become guardrails. What these platforms could not give us in late October was a full spectrum and a close look at structure. They were never built for that. Their job was to see through glare and say something is happening here. They did that. Now the baton passes. As the object pulls away from the sun in December, telescopes that read lines instead of colors, and cameras that resolve fine structure instead of wide halos will get their turn. The first act belonged to the coronagraphs. The next act belongs to the spectrographs and imagers waiting in the wings. Start with the oldest rule in space science. If something seems astonishing, assume your instrument is playing a prank until it proves otherwise. Near the sun, pranks are common. Stray light slithers through the optics and paints faint halos where nothing exists. Vignetting makes the center of a frame look healthier than the edges, and that bias can tilt color. Detectors bend their own rules at the bright and dark ends, turning linear response into a curve that whispers lies. Cosmic rays drop pinpricks of fake stars into single frames and then vanish. Even the sun itself throws moving patterns across the field that look suspiciously like visitors. Engineers and analysts do not chase ghosts with hope. They bring checklists. First, they test for saturation. If a pixel hits its ceiling, the true brightness hides above that cap. The cure is shorter exposures and cross-checks with instruments that did not clip. Next, they test for nonlinearity. Detectors respond less than they should at one end or more than they should at the other. Calibration lamps and stable stars define how to straighten that curve, and those maps are applied before anyone trusts a number near perihelion. Then comes background building. The solar corona is a restless quilt. You build a rolling average of many frames to capture the quilt and subtract it, leaving only the newcomers that move across the pattern. Do this with different window sizes and compare. If your result depends on a particular subtraction recipe, caution flags go up. If the moving source survives many recipes with roughly the same brightness and color, the flags come down one by one. Color deserves its own trial. Filters age. Coatings change a little under radiation and thermal cycling. Teams maintain response curves for every filter wheel and detector channel. A solid test asks whether the blue tilt follows the object as it crosses the field. If the color flips or fades at the same detector coordinates, regardless of where the comet sits, that smells like vignetting. If the color remains steady while the comet moves, the bias is less likely to live on the detector and more likely to live in the sky. Optical ghosts are another villain. Light from bright sources just outside the frame can reflect inside the instrument and conjure false shapes. Ghosts betray themselves by staying tied to the instrument rather than the stars. Rotate the pointing a little and watch. Real targets cling to the star field. Ghosts slide or distort with the optics. This is why different vantage points matter so much. A ghost in one instrument will not repeat in another that uses a different optical train and sits in a different orbit. Temporal coherence is a quiet superpower. A random artifact will spike and vanish. A real object will rise and fall smoothly as geometry demands. The geostationary sentinel brings rapid cadence, so analysts can throw out one-frame flashes and keep only trends that persist across many minutes and hours. The veteran coronagraph brings stability, so drift and long-period noise are well understood. The Pathfinder brings parallax, so a moving point is easier to separate from coronal features that are welded to the Sunday skepticism also asks for adversarial tests. Swap pipelines between teams and see if independent code extracts the same numbers from the same raw frames. Mask the comet region and estimate backgrounds from different annuli. Vary the photometric aperture and check how totals change with radius. Reprocess subsets with blind labels so the analyst does not know which frames are supposed to be bright. Each test tries to break the result. What refuses to break grows more believable. None of this makes romance illegal. It makes it earned. If the blue ratio remains when you correct for vignetting, if the brightness curve survives shorter exposures that dodge saturation, if the signal walks across the detector with the object and not with the optics, and if a second instrument with different scars tells the same story, then the default explanation shifts. The burden moves from prove it is real to prove it is not. That pivot is not an invitation to leap to the most dramatic idea on the menu. It is a license to ask better questions. If instruments are not fooling us, what process could sustain a light surge so steep without obvious thrust? If color is not a calibration quirk, what atoms or grains are radiating, and why at that scale? Good skepticism never says do not wonder. It says aim your wonder through cross-checks until only the sky is left to answer. Begin with the simplest bold idea. 3i Atlas is natural yet unusual. A body loaded with super volatiles that wake early, rage hard near the sun, and flood space with glowing gas. In that picture, the nucleus carried large stores of carbon monoxide and carbon dioxide locked beneath a tough crust. As the heat rose toward perihelion, pressure built in hidden pockets until the skin fractured and the reservoir vented. Gas expanded, molecules were pumped by sunlight, and the visible emission lit up the coma. You are not watching sunlight bounce from dust. You are watching the object write its own light. There is a reason this idea attracts sober scientists. We have seen carbon dioxide-rich comae before, just not often at this intensity. Carbon dioxide sublimates at temperatures colder than water ice, which means activity can begin far from the sun and then climb steeply as the object dives inward. Add carbon monoxide, which is even more volatile, and the gas load rises again. If the crust is strong enough to bottle that pressure until close approach, the late release can look abrupt, like a valve opening at a threshold temperature. That is a recipe for a brightness curve that bends from gentle to fierce in a short span. Gas explains the color, without strained metaphors. Cyanogen glows in the violet. Diatomic carbon paints green bands that leak toward blue. Oxygen can add a sharp feature near the blue-green. A coma that is thick with these species under a brutal ultraviolet field can push the color ratio to the blue side, even when there is not much fresh dust. It is not that the dust became magical. It is that the molecules drowned the dust in their own light. A luminous envelope that spans hundreds of thousands of kilometers fits this view because gas expands quickly and fills space in a way dust cannot match without dragging along a world of particles. Surface physics matters. A mixed crust of refractory organics and dust can act like an insulating blanket. It keeps subsurface volatiles cold and stable until enough heat soaks through to destabilize the structure. Fractures propagate, vents open, jets form, and the sun sees more effective surface area in an instant. That can mimic fragmentation without shattering the nucleus into obvious chunks. To a camera, the brightness jumps as though the object multiplied. In reality, the facing area multiplied while the body stayed mostly intact. The skeptic will ask about force. Gas leaving the surface should push the nucleus the way exhaust pushes a rocket. Where is the shove? The super volatile story has an answer that does not clutch at straws. If the venting is roughly symmetric over a rotation, the tiny thrusts cancel. If the jets fire from many places at once, the vector sum is small, even though the gas output is large. You get a bright coma with weak non-gravitational acceleration. That is not a contradiction. It is geometry and spin doing quiet work. Predictions are where this idea earns or loses ground. Spectroscopy in visible and infrared light should show classic lines if gas is king. Cyanogen in the violet. Diatomic carbon in the green. Oxygen near 500 nanometers. Carbon monoxide bands near 4.7 micrometers. Carbon dioxide near 4.3 and near 15 micrometers. The relative strengths of those bands translate into production rates and gas-to-dust ratios. A gas-dominated coma should also polarize light weakly compared with a dust-dominated coma, because emission lines are not strongly polarized the way scattered sunlight is. High time, resolution could add a twist. If venting ties to rotation, periodic flickers may ride on top of the overall glow. Fragmentation remains a live branch on this tree. If the nucleus cracked into several pieces near perihelion, surface area would jump, and so would the gas supply. In that case, high-resolution imaging in December could reveal companions that drift slowly apart. Even if fragments are too small to separate cleanly, subtle shape changes in the inner coma could betray multiple sources. Radar would be a decisive arbitrator, if geometry and strength permit, since a loose rubble pile returns a softer echo than a compact shard. The supervolatile path carries its own limits, and those are healthy to name. To drive a light curve as steep as the negative 7.5 estimate, the gas production has to climb very rapidly in the final approach. That demands either a storehouse of volatiles larger than is typical, or a release valve that stayed closed until the last mile and then opened wide. Nature can do that with layered crusts and phase changes, yet it is not the default for most comets. The burden is not proof beyond doubt, but it is proof with lines and numbers, not just adjectives. There is also the color map. If gas emission paints the show, color should look strongest where the gas is densest and freshest. Expect the bluest ratios near jet routes and along flows shaped by the solar wind, not simply where a dust fan would scatter sunlight. Instruments that can map color across the coma will tell us whether the blue draws a gas geography or a dust geometry. That is a test a narrative cannot dodge. So Hypothesis A walks forward with its palms open. It keeps everything natural, uses molecules we already know, and leans on physics that has lit many comets at gentler levels. It demands vigor and timing rather than magic. If December spectra shout the right lines, if polarization stays low while color stays blue, if the light curve settles onto a track that looks like outgassing sustained without wild thrust, this explanation will feel less like a story and more like a diagnosis. And if those lines fail to appear, the hypothesis will bow and make room for harder questions. Picture the sun as a vast engine that breathes a wind of charged particles. When that wind slams into a cloud of neutral gas around a comet, the impact can make the cloud glow. Not by reflection, but by direct electrical excitement, the way a neon sign lights when electrons accelerate through a tube. If 3I Atlas carried a deep envelope of gas near perihelion, the solar wind could have turned that envelope into its own light source. That would explain a color tilt toward blue and an extended glow that does not fade the way dust reflections usually do. A few terms in plain language. Plasma is gas so hot that atoms fall apart into free electrons and ions. The solar wind is plasma streaming outward from the sun at hundreds of kilometers per second. Where that wind meets a comet's neutral gas, several things can happen. Fast electrons can collide with atoms and molecules and kick their electrons to higher energy. When those electrons fall back, they emit light at sharp colors called lines. Ions from the wind can also steal electrons from neutral atoms in a process called charge exchange. That produces excited atoms that radiate as they relax. Both paths are real. We have seen them in softer forms around many comets, especially in X-rays and faint visible glows far from the Sunday. Move the battle close to the sun and the energy available climbs. Why blue? Some of the strongest visible lines and bands for common cometary species cluster in the blue and blue-green. Oxygen emits a well-known line near 500 nanometers. The cyanogen family paints violet. Diatomic carbon contributes in the green and can bleed toward blue. Electron impact and charge exchange can populate the upper states that feed these lines. If you pack a large volume with gas and bathe it in a furious wind, the integrated light across hundreds of thousands of kilometers can be bright and skew blue without asking dust to do the heavy lifting. The shape of the glow can help. Think of a bow wave that builds in front of a ship. A fast wind against a dense coma should pile energy into a curved shell, upwind from the nucleus, then sweep charged material into a tail downwind. If plasma is driving the show, the color should map onto that geometry. Bluer along the nose, where electrons dump the most energy. Structured along the flanks where magnetic fields channel flows. That is very different from a dust fan lit by reflection, which would track sunlight direction and grain dynamics rather than wind energy. Time behavior is another tell. Plasma processes respond quickly to changing space weather. When the solar wind speed rises, or when a magnetic sector boundary passes, the glow can brighten or fade within minutes to hours. Reflection by dust does not pivot that fast because dust production and transport are slower. If the perihelion color and brightness climbed in step with known wind changes, that would argue for plasma. If they ignored the wind and followed only distance to the sun, that would argue against it. There is also a comfortable answer to the force problem. Plasma-driven emission shines by energy deposition in gas that is already there or is being supplied in a broadly symmetric way. It does not require one-sided jets strong enough to shove the nucleus off its track. That is why you can have big light without big thrust. The nucleus coasts, while its halo takes the beating and glows. This path does carry demands. You need a generous supply of neutral gas to interact with the wind. You need that supply to persist across the perihelion window rather than flash and vanish. You need energy deposition high enough to light visible bands across a giant envelope, not just a thin skin near the core. Those requirements are steep, but not absurd near the sun, where ultraviolet light is fierce and electron densities climb. The burden is to show that the energy budget and the gas supply pencil out. Tests in December can push this hard. Spectra should show line-rich emission rather than a smooth continuum. Ratios of lines that are sensitive to electron impact, such as oxygen near 500 nanometers versus neighboring bands, should rise in a way that matches basic plasma models. Polarization should stay low where emission dominates and should vary across the coma in a pattern tied to wind direction rather than to simple scattering angles. Rapid photometry should find brightness changes linked to solar wind monitors that taste the flow upstream of Earth. High-resolution images should sketch a bow-shaped front and a structured downwind region, not just a broad dust fan aligned with sunlight. What would hurt this idea? A spectrum that is mostly featureless and looks like reflected sunlight would be a blow. A color map that shows blue only near the core and not along a wind-shaped shell would be a blow. A light curve that ignores wind changes, while the wind itself is obviously roaring, would be a blow. Plasma is a bold but natural way to make blue and bright near the Sunday. It wins if the sky behaves like a storm front hitting a cloud. It loses if December reveals a quiet field with scattered dust doing most of the work. So, Hypothesis B stands ready for trial. It explains an extended blue glow without exotic dust and without exotic engineering. It predicts fast changes, wind-aligned structure, and crisp spectral lines. If we see those, the storm is real. If we do not, the storm fades, and we return to molecules or to the hard edge of stranger ideas. Either way, the wind will have helped us sort truth from temptation. Hold this as a disciplined what if. Suppose 3I Atlas is not only rock, ice, and gas. Suppose a fragment within it carries materials shaped by minds, built to endure and to react only under brutal stellar conditions. Not a claim, a thought experiment. What design choices would make sense for something that must coast for ages, sleep through radiation, then wake only when the sun is close enough to flood it with energy? Start with the material. Engineers would favor refractory substances that laugh at heat and shrug at vacuum. They might embed optical coatings that fluoresce under hard ultraviolet light, both as sacrificial shields and as status flags. They might include microstructures that switch state at a specific radiant flux, like a thermostat with a cosmic threshold. In that frame, a perihelion surge is not a panic, it is a trigger. Cross the line, and the surface enters a different optical and thermal regime that makes blue light, and lots of it. Why blue? Artificial phosphors are good at narrowing light into chosen bands, and some will radiate strongly in the blue and blue-green when pumped by ultraviolet. Thin film stacks can also shift reflectance and emissivity sharply, with angle and wavelength. A device meant to signal its passage near stars could trade long life for a bright pulse at each close approach, glowing where detectors in a young civilization are likely to look. That is speculation, yes, but it makes specific promises. Narrow lines, steady colours not tied to common comet gases, and a brightness surge without the dusty mess of mass loss. Geometry tells more stories. Manufactured surfaces often prefer planes, edges, or repeating patterns at small scales. If the nucleus hosts a shard with symmetry, the inner coma might show persistent, cleanly edged jets, or reflections that repeat with rotation in clockwork ways. Fragmentation would not look like a crumbly avalanche. It would look like pieces that keep angles. High-resolution imaging in December could catch such regularity if it exists. Planetary radar, if geometry and power allow, could notice a radar albedo closer to metal than to fluff. Force is the quiet ally here. A glowing coating does not shove a nucleus. A fluorescent lattice does not blow like a rocket. If light rises while the path stays pinned to gravity within tight error bars, the engineered picture wins a subtle point. That is not proof. It is consistency. The stronger the light surge without thrust, the more we ask whether emission rather than expulsion carried the show. What would count as extraordinary evidence? Spectra that display narrow features at wavelengths not owned by known atoms or common molecules. Coupled line ratios that remain stubbornly fixed as the object rotates and as distance changes, like a lamp with a regulated driver rather than a gas with changing temperature and density. Polarization that maps as if from smooth-oriented surfaces rather than random grains. Photometric modulations that repeat with a period like a machine's heartbeat and hold phase across many rotations. Any one of these would be arresting. Two together would. Make the air thin. Now the cold water. Priors matter. The number of natural comets we know is vast. The number of confirmed artificial interstellar objects is 0. A sane prior assigns a tiny probability to engineering and waits for violent evidence to move that number. Occam's razor still slices in favour of chemistry and plasma first, not because imagination is illegal, but because simplicity wins until facts demand complexity. An engineered hypothesis that cannot beat natural models head-to-head does not deserve the headline. This is also where fakes go to die. If narrow features line up with cyanogen and diatomic carbon after all, the phosphor dream collapses. If color maps follow gas density and wind geometry rather than surface orientation, the technosignature fades. If the light curve breathes with distance to the sun but not with any internal clock, the machine heartbeat is just wishful rhythm. A thought experiment does not get a free pass. It gets a sharper knife. So why? Keep the door open. Because dismissing possibilities too early blinds us to simple tests that cost little and teach much. December offers those tests. We can ask telescopes to search for lines that belong to coatings rather than to gases. We can look for geometric regularity in the inner coma. We can watch for stuttering brightness that tracks a precise rotation and refuses to smear out. If nothing strange appears, the engineered branch trims itself and we move on cleaner. If even one decisive pattern lands, the world changes in slow motion as teams replicate and confirm. Hold curiosity and caution in the same hand. The engineered activation idea is a lens, not a verdict. Use it to focus questions that natural models do not think to ask. Then let the sky grade the paper. Either we find the fingerprints of design and step into a new chapter of astronomy, or we learn again that nature has more tricks than we gave her credit for. Both outcomes dignify the question. Both honor the evidence. Science is a tapestry, and every beautiful tapestry has loose threads. In the weeks around perihelion, reports landed that seemed to argue with each other. An antitail apparently lengthened on a 24-hour timescale. Orbital positions showed tiny residuals that hinted at weak, non-gravitational pushes. Some early photometry claimed little or no perihelion flare at all. How do you hold those in the same head as a blue, bursting glow seen by spacecraft? You start by asking whether everyone was measuring the same thing, in the same way, at the same time. They were not. Begin with the antitail. Despite the name, nothing physical points toward the Sunday dust grains released earlier, follow curved paths under gravity and radiation pressure. When Earth, Sun, and comet line up just right, those backstreaming grains project as a short wedge that seems to aim sunward. Change the viewing angle a little, and the wedge grows or shrinks, even if the dust supply does not change. If a real puff of fresh dust arrives on top of that geometry, the apparent growth can look dramatic. That is a dust story told by perspective, not a gas story told by light. Brightness at perihelion is a gas and emission-heavy story. Gas glows, dust scatters. Cameras that emphasize the near-sun halo and color ratios will be hypersensitive to gas emission. Telescopes tuned to study dust fans and tail morphology care about grain size and direction. It is not a contradiction for a dust feature to evolve modestly while gas emission jumps. You can turn up the music in one room while the hallway stays quiet. Different instruments were listening to different rooms. Now, the tiny orbital residuals. If outgassing thrust were large and one-sided, the nucleus should drift from the gravity-only path by enough to measure cleanly. Reports so far suggest subtle offsets, the kind you can lose in noise on a poor night and recover on a good one. Symmetric venting smears thrust around the compass and cancels itself. Emission-dominated light does not require mass loss that kicks hard. Those facts make weak residuals surprisingly compatible with a bright blue coma. The light can be loud without the shove being strong. What about the claims of minimal flare near closest approach? That is where geometry and method can betray you. From the ground, the object sank into daytime glare and low-altitude air. Backgrounds rose, contrast fell, and short exposures to protect detectors also starved the faint end of the curve. A brightness spike confined to hours can hide in gaps between safe observing windows. Spacecraft that stared continuously with coronagraph masks saw a curve the ground could miss. No one lied. They watched different windows with different glass. A clean way to reconcile the set is a state change close to the Sunday. For months, the object behaved like a fairly active comet. Some dust, some gas, nothing sensational. Near perihelion, a thermal or structural threshold was crossed. Subsurface pressure outran strength, vents opened, a sheath of gas thickened, and plasma or fluorescent pathways took over the light budget. Dust geometry barely flinched, so anti-tail metrics drifted according to perspective and modest dynamics. Gas-dominated color and brightness surged, so coronagraph photometry jumped. Thrust stayed small because the new activity was either broadly distributed or short-lived and symmetric over a spin cycle. There is also the unromantic alternative that some early numbers were simply wrong by ordinary margins. Near the sun, photometry gets cranky. Sky subtraction bites. Catalogue stars used for calibration are scarcer near bright daylight. A few mistaken points can paint a flat line where a rising curve would be. The cure is not scorn. It is replication with better geometry and honest error bars when the object re-emerges into darker skies in mid-December. The rule that keeps us sane is that contradictions often dissolve when you separate dust from gas, emission from reflection, and geometry from physics. An anti-tail is a projection. A blue coma is a spectrum. A weak residual is a sum of tiny arrows that can cancel. Tie each measurement to its domain, and the story stops shouting at itself. It becomes a layered picture of one body moving through different regimes. That is why the next campaign matters. We will map colour across the coma to see whether the blue sits where wind and gas should rule, or where dust should shine. We will track position with enough precision to measure any quiet shove and tie it to light changes. We will image dust structures with stable backgrounds while the sun is out of the frame. If those pieces click, the loose threads will braid into a single rope, and the puzzle will feel less like an argument and more like a chorus. 5 weeks can feel like a lifetime in space news, yet those weeks are exactly what turn panic into knowledge. As 3i Atlas climbs out from the sun's glare, the geometry begins to favour us again. The separation between the object and the solar disk widens a little each dawn and each dusk. That small change is everything. It lowers backgrounds, opens longer observing windows, and invites instruments that could not safely participate during perihelion to join the hunt. Think of the path ahead as a relay with many legs. Wide-field imagers pick up the motion and nail down the track against star fields. Medium apertures gather photometry that stitches a fresh light curve from night to night. Big mirrors and space observatories pursue spectra and polarimetry that carve the colour into components. No single team can do all of it. The win comes from overlapping coverage that lets one line of evidence cross-check another. For professionals, the plan is straightforward and intense. Spectrographs on major telescopes will sweep visible and infrared bands to search for lines that betray gas species and their production rates. Polarimeters will test whether light is strongly polarized as scattered sunlight would be, or weakly polarized as pure emission would be. High-cadence imagers will watch for short-term flickers that could reveal rotation or wind-driven variability. All of it will be tied to precise astrometry, so that any small orbital drifts can be correlated with changes in brightness or color. For the amateur community, this is a rare chance to contribute signal that matters. Small and medium telescopes with careful calibration can measure brightness night after night and provide the dense time sampling that large observatories cannot afford. Stacking short exposures can lift the faint coma above the noise without pushing equipment into dangerous territory. The key is discipline. Use dark sites where the twilight glow is low. Follow vetted ephemerides from trusted sources. Share data through established networks that collate and compare results. Safety is a hard rule, not a suggestion. Never aim optics near the sun, unless you are using certified solar filters and procedures designed for daylight observing. Even after sunset or before sunrise, respect the limits. If the object sits too close to the solar disk on a given date at your latitude, stand down and wait for a safer window. There is no discovery worth a damaged eye or a scorched sensor. The sky will still be there tomorrow. Timing, angle, and distance dictate what each night can deliver. Early in the 5-week span, the object may be accessible only in a thin wedge of twilight with low altitude and a thick slice of atmosphere in the way. That favours bright broadband photometry over deep spectroscopy. As days pass, the altitude improves and the line of sight clears. Spectra become cleaner. Polarimetry gains leverage. Toward mid-December, the balance tilts from merely possible to genuinely productive. We also prepare for weather in space. The solar wind does not care about our scheduling. If plasma processes are part of this story, their signatures may wax and wane with solar activity. That is why coordination with space weather monitors matters. When an upstream spacecraft reports a jump in wind speed or a shift in magnetic sector, ground teams can check whether the coma brightened or changed color in step. Correlation is not proof, but tight timing is persuasive. Expect a living dashboard rather than a single headline. Curves will update, maps of color will refine. Predictions written now will be tested publicly, and where wrong, corrected in public as well. That transparency is not a weakness. It is the culture that prevents us from chasing mirages long after they fade. Viewers can follow along without needing a graduate seminar. Did the blue hold under better geometry? Did the light curve flatten or keep its fierce slope? Did any measurable shove appear in the path? There is a deeper reason these 5 weeks matter. Pressure makes models honest. Before December 19, every camp must write down what would change their mind. The natural chemistry camp must specify line strengths and gas-to-dust ratios that would be decisive. The plasma camp must outline variability and geometry that would clinch their case. The engineered thought experiment must name signatures that would count as extraordinary evidence and admit what absence would close that door. When prediction meets measurement, bluster goes quiet. Keep an eye on cadence and coverage. A few spectacular spectra will not replace the need for steady nightly photometry. A handful of beautiful images will not replace the need for careful polarimetry. The power of this campaign will come from unglamorous repetition and from many eyes comparing notes without ego. That is how a brief show near the sun turns into a clear answer for the rest of us. So the countdown is not a drumbeat to drama, it is a schedule for clarity. Each dawn and dusk we gain a little more sky, a little more leverage, and a little more truth. By the time December 19 arrives, we will not be waiting for a miracle. We will be ready for an answer, whichever way it falls, because we built the questions in advance and set them where the sky could see them. Stand at the fork with me. Ahead lie two clean paths, and either one will teach us something we cannot learn any other way. Down the first path, 3i Atlas keeps shining. Maybe it even climbs a little as geometry improves. The color stays stubbornly blue. Spectral lines stand tall night after night. The coma holds its size or swells slowly, and surface brightness refuses to sag the way dust reflection usually does. Photometry from small and large telescopes agrees within honest error bars. Astrometry says the orbit is still almost gravity only, with no hefty shove, bright and blue without a strong push. If the light holds, the story tilts toward processes that feed on energy rather than on geometry alone. That means ongoing gas production pumped by sunlight into emission, or plasma energy pouring into a giant envelope. In this future, spectra should become a forest of lines. Cyanogen would keep singing in the violet, diatomic carbon would hold its green band, oxygen would keep its blue-green spike, infrared instruments would measure carbon dioxide and carbon monoxide with the confidence of a barcode scan. Polarization would stay low or map in patterns that do not match simple scattering. Rapid sequences might show flickers tied to the solar wind or to rotation, but the baseline would remain high. A sustained glow also tests the force puzzle. If brightness stays loud and the path stays quiet, then the light is not coming from a one-sided rocket of dust and gas. It is coming from emission that does not shove, or from many vents that cancel their own pushes over a spin. That combination trims the tree of explanations. Natural chemistry survives if the gas budget matches the lines. Plasma survives if wind-aligned structures and fast responses appear. The engineered thought experiment keeps a narrow foothold only if spectra misbehave and geometry looks manufactured. Most roads in this bright future point to nature doing something extreme yet lawful. Now the second path. The light collapses. Within days or a week, the coma fades by many whole numbers in magnitude. Color drifts back toward neutral. Lines shrink or vanish into the noise. The envelope that looked like a shell becomes a ragged puff that only big mirrors can see. In that future, fragmentation or exhaustion is doing the talking. A crust may have cracked, dumped a reservoir of gas, and then sealed or emptied. A fragile nucleus may have shed a skin or broken into small pieces that cool fast and stop feeding the glow. The steep perihelion curve becomes a spike, not a plateau. A fast fade does not erase what we learn near the Sunday. It reframes it. The negative 7.5 slope becomes the signature of a transient release rather than of a sustained regime, gas-dominated. Light makes sense if the reservoir emptied quickly. Blue color makes sense if the near-sun bath pumped lines for a short window, and then the pump and the fuel parted ways. Weak orbital residuals remain compatible if the venting was brief or symmetric. In this future, the task is to catch the afterglow and the debris. High-resolution images could show soft trails or small companions, even if faint. Infrared instruments might still find warm dust that remains after visible light has dwindled. Radar would have a better chance of silence because fluffy fragments scatter weakly. There is a third, narrow lane between those two. The visible could dim while the infrared stays lively, as larger grains keep radiating heat even when blue emission fades. Or the opposite could happen, if fresh gas keeps glowing while dust production falls. Mixed outcomes do not save ambiguity, they refine it. They tell us the budget of gas and dust and how each evolves after the peak. Either way, the theory, space collapses. A bright plateau punishes models that depend on one-time fireworks and rewards models with continuous energy input. A fast decline punishes models that require ongoing pumping and rewards models that turn on and then shut down. The point is not to win a bet, It is to cut away ideas that cannot survive public data. So we set simple expectations that anyone can track. If the object stays bright, lines should stay strong, and polarization should stay low. If the object fades, lines should weaken first or together with the continuum, and the color should drift toward the Sunday. If the path stays clean of strong non-gravitational shove in both futures, the light is not a rocket, it is a lantern. When the next clear night comes, the sky will pick a lane. We will follow, not with drama for its own sake, but with the relief that comes when a fork becomes a road. When light is split into its colors, the universe stops guessing. Spectroscopy is where stories either stand, up straight or fall over. For 3i Atlas, the test is simple to say and hard to fake. If gas is carrying the show, we should see sharp fingerprints at exact places in the spectrum. Cyanogen leaves a violet signature. Diatomic carbon paints strong bands in the green that can lean toward blue. Neutral oxygen adds a spike near 500 nanometers. In the infrared, carbon monoxide sits near 4.7 micrometers and carbon dioxide sits near 4.3 and 15 micrometers. Find those clearly, and the blue glow becomes chemistry in motion, not a trick of dust. The Hubble Space Telescope and the James Webb Space Telescope were built for this kind of decision. Hubble can comb the visible range where violet and blue features live, resolving line shapes that separate emission from reflection. Webb reads the infrared with a steadier hand than anything before it, and can weigh carbon monoxide against carbon dioxide by measuring both bands at once. Together they can tell us what molecules are present, how much of each, and whether the mix changes with time. If the spectrum is a forest of lines on top of a dim continuum, emission is king. If the spectrum is mostly smooth with gentle tilts, reflection is back in the game. Line ratios speak louder than any single line. The strength of cyanogen compared with diatomic carbon says something about chemistry. The strength of oxygen compared with the nearby continuum says something about how energy is being deposited into the coma. In the infrared, the relative heights of carbon monoxide and carbon dioxide bands translate to production rates and temperatures. Those numbers are not decoration. They are the budget that tells us whether the object could power a brightness surge as steep as the one inferred near perihelion. Motion hides inside lines as well. If jets are blasting, some lines will be shifted slightly toward the blue or toward the red as gas flows toward or away from us. If the coma is broadly symmetric, the average line centers will sit where physics says they should. If plasma is at work, some lines can broaden in ways that reflect electron energies and collisions. A narrow, stable line from a coating would behave differently from a wide, lively line from a storm of particles. The shapes teach as much as the heights. Spectra can time the heartbeat of a nucleus. Take repeated exposures through one night and through many nights. If the light is tied to rotation, certain lines will rise and fall with a period, and keep that phase as days pass. If the light is tied to space weather, the lines will respond to changes in the solar wind and then relax. If the light is a simple reflection story, the lines will be weak and the continuum will bend gently in color without sudden spikes. The rhythm is a clue that diagonally cuts through competing ideas. Polarimetry works like a lie detector next to the spectrograph. Scattered sunlight is polarized in ways that depend on grain size and viewing angle. Emission lines are not strongly polarized. Measure polarization across wavelengths and across the coma while you measure lines, and the two pictures either dovetail or fight. Strong lines with weak polarization point to gas glowing on its own. Weak lines with strong polarization point to dust, borrowing sunlight and sending it back our way. We watch for one more thing that natural models and engineered thought experiments handle very differently. Natural gas lines breathe with distance and with changing temperature and density. Engineered phosphors would tend to keep narrow, stable colors that do not care much about those slow changes. If December delivers narrow features that refuse to shift, and if those features do not match catalogs of known atoms and molecules, the conversation would change tone fast. If the features line up with cyanogen, diatomic carbon, oxygen, carbon monoxide, and carbon dioxide, the conversation becomes a careful accounting job. Extreme, yes. Exotic, not required. All of this can be grounded in simple outcomes that anyone can follow. If the visible spectrum shows strong violet and blue-green features, and the infrared shows firm bands from carbon species, gas is doing the heavy lifting. If lines are weak, and the color returns to the sun while polarization rises, dust has taken the stage. If brightness remains high while lines stay sharp, and the object's path shows no strong shove, emission without heavy mass loss is the winner. We do not need mystery to get a satisfying answer. We need clear lines, honest ratios, and enough patience to let the sky speak in its native language. When the first spectra land, resist the urge to skim. Look for the spikes, look for the ratios. Look for whether the same shapes appear in different instruments and on different nights. The spectrum decides. It always has. It will again here, and the answer will either be a bold chapter in comet chemistry, a storm-coloured lesson in near sun, plasma, or a short list of questions that demand we look twice at our assumptions. The light is already on the way. Light carries a hidden handshake. When it bounces from tiny grains, its electric field lines tend to line up in preferred directions. That alignment is polarization, and it turns a pretty glow into a measurement you can test. If 3i Atlas is blue because sunlight is scattering off very small dust, the scattered light should be polarized in ways that depend on grain size, shape, and the angle between sun, object, and observer. If the blue is mostly gas emission or plasma-driven light, polarization should be weak and often structureless. The twist in the light tells you who is speaking. Start with the phase angle, the angle at the comet between the sun and Earth. For dust that is small compared with visible wavelengths, polarization strength usually rises from small phase angles to a broad maximum, then falls again as the geometry becomes backlit. The location and height of that maximum depend on the size distribution and how compact or fluffy the grains are. This provides a fingerprint. A coma rich in submicron grains tends to show stronger polarization near the peak, with a smooth wavelength trend that bends slightly toward blue. Now, fold in wavelength. Scattering by very small grains often polarizes blue light a bit more than red because short wavelengths interact more strongly. Emission lines do not follow that rule. They are created rather than reflected, so they arrive largely unpolarized, unless they are mixed with scattered continuum light. Measure polarization in a blue band where emission is strong, and in a neighboring red band where emission is weaker. If the percentage drops in the blue while intensity rises, emission is taking over. If polarization lifts in the blue together with intensity, dust is doing real work. Maps matter as much as totals. If dust rules, the strongest polarization often forms rings or fans that follow the pattern of jets and the direction set by radiation pressure. If plasma or pure emission rules, polarization maps flatten and become noisy, while color maps show blue spread broadly across the envelope. Combining the two lets you draw a boundary around the domain of each process. The inner coma might glow with low polarization where gas is thick, while farther out a polarized shell betrays sunlight scattered by grains that wander beyond the dense core. There are confounders, and they are worth naming. Mixed light dilutes polarization. If a polarized dust continuum and an unpolarized emission line land in the same filter, the measured percentage drops even if the dust signal anchors the shape. That is why observers use narrow filters centered on lines and narrow filters that avoid lines, then compare. Multiple scattering inside a very dense coma can also depolarize light, because random paths scramble the preferred direction. Careful modeling helps separate dilution from genuine absence. Instrumentation brings its own discipline. Polarimeters measure tiny differences in brightness along different orientations of a rotating analyzer. Stability matters. So does calibration using stars with known polarization and stars with nearly none at all. Repeat measurements as the object moves across the field catch any detector quirks. If the pattern rotates with the sky rather than with the comet, the instrument is whispering. If the pattern rides with the coma and shifts with phase angle as nights pass, the comet is speaking. Tests for December are clean enough for anyone to track. If the blue remains strong while measured polarization stays low in the same regions, emission dominates. If polarization rises to values that match classic dust phase curves and tracks the expected angles around the nucleus, dust is driving the visible light. If polarization is patchy and lines up with jets and fans seen in broadband images, tiny grains are present in large numbers. If it remains flat and faint while spectra brim with lines, molecules and electrons are carrying the torch. The result also feeds the force question. A dust-heavy coma built by powerful jets should leave some non-gravitational signature unless the jets are balanced over a spin. An emission-heavy coma can be bright without momentum transfer. High polarization, together with measurable orbital residuals, would push models toward active venting and perhaps toward fragmentation. Low polarization, together with a quiet orbit, would point to radiative processes and symmetric release. One more payoff hides here. If the engineered thought experiment were true and smooth-oriented surfaces contributed, polarization could rise in a way that stays unusually stable with wavelength and geometry, more like light from a prepared film than from random crumbs. That would be a surprising pattern and would demand fierce replication. Absent that, ordinary dust and gas remain the likeliest authors of whatever twist we see. By itself, polarization will not close the case. Paired with spectra and photometry, it becomes a lever that moves heavy doubts. It tells us whether the blue we admire is a coat of dust catching sunlight or a lantern of gas lit from within. It is the quiet measurement that confirms what color only suggests. Over a few clear nights, with the phase angle shifting and the coma breathing, that hidden handshake will either tighten or relax. When it tightens, the dust story hardens. When it relaxes, emission takes the lead. Either way, the twist turns light into a verdict. If light is the show, motion is the truth behind the curtain. A comet that vents gas is a tiny rocket. Every molecule that leaves the surface carries momentum, and the nucleus should recoil a little. Astronomers hunt for that recoil the same way sailors read a current by watching buoys drift. Night after night, they measure the position of 3I Atlas against background stars and compare it with where pure gravity says it ought to be. The difference, even when it is a fraction of an arc-second, is a signature of non-gravitational acceleration. Turn that idea into something you can feel. Imagine tossing pebbles off one side of a canoe. The boat slides the other way. If you toss pebbles in every direction with equal enthusiasm, the motions cancel and the canoe sits still. Comet jets work the same way. One-sided venting moves the orbit measurably over weeks. Many jets spread around a spinning body can cancel their own pushes. That is why a bright coma does not guarantee a large orbital shove. Force depends on direction and timing as much as on total mass lost. Radiation pressure is the other invisible hand. Sunlight itself pushes on dust and very low-density fragments. The smaller and lighter the particle, the stronger the effect compared with gravity. Dust tails bend because the sun is blowing on them with photons. For a compact nucleus, the effect is tiny, yet, if 3I Atlas shed clouds of very small grains, some part of the measured motion of the envelope could be shaped by that push. Astrometry focuses on the nucleus, not the halo, but separating a faint core from its glow near the sun is hard. Clean geometry in December will help isolate the body and reduce confusion from dust that sails when light hits it. How do you convert those tiny position differences into physics? Observers fit a model that adds a gentle thrust term to the gravitational equations and solves for its size and direction. If the fit improves dramatically and the derived thrust lines up with the sun or with an active jet, you have a physical story. If the fit barely improves or points in nonsense directions, noise and systematics are still in charge. Correlating any measured shove with changes in brightness or color is the next link in the chain. If a surge in light comes with a consistent tweak in the path, venting has likely changed. If light surges while the path does not, emission without mass loss is back in the lead. Rotation complicates and clarifies. A nucleus that spins can sweep jets through space like lawn sprinklers, averaging their thrust over a turn. That can flatten what would otherwise be a jagged acceleration curve. It can also imprint a weak periodic wiggle that long strings of precise positions can detect. Combine high-cadence astrometry with rapid photometry, and you can test whether any wiggle in the path shares a period with brightness modulations. Shared timing says vents tied to rotation matter. No timing link says the light may be coming from a process that shines without pushing. Radar is the blunt instrument that can settle structure when geometry cooperates. A powerful transmitter on Earth sends a radio pulse toward the target. A faint echo returns after a known delay. The delay gives distance. The spread in frequencies gives rotation. The strength of the echo hints at surface properties. Fluffy, low-density ice and dust scatter weakly. Dense, metallic or rock-rich surfaces scatter strongly. For a small, fast interstellar object, radar is a reach, because you need closeness, time on a big dish, and a coma that does not absorb the signal. Still, a marginal detection can distinguish a compact shard from a porous snowball, and can bound the size and spin rate, even if images do not resolve shape. There is a paradox worth savouring. If 3i Atlas lit up through a mission that did not eject much mass, radar might still return a decent echo from a largely intact nucleus, while astrometry shows almost no thrust. That pairing would tilt the interpretation away from explosive mass loss and toward radiative processes that paint the coma without launching a rocket. If instead the light surge came from many fresh vents or from subtle fragmentation, radar could catch a rougher, larger cross-section, while astrometry records a small but consistent push aligned with the Sunday. Noise is not the enemy when you know its voice. Low-altitude air near twilight blurs positions. Background stars thin out near the sun, making calibration trickier. Teams beat those problems with repetition, and by sharing residuals so outliers can be flagged. Confidence grows when independent observatories on different continents, in different air, find the same tiny drift. Confidence grows again when that drift evolves in a way that matches a simple physical picture, rather than a coincidence of bad nights. The most useful outcome is not a dramatic kick. It is a clean limit. If after weeks of careful measurement the allowed non-gravitational acceleration is tiny, then any model that needs a strong one-sided jet is in trouble. If the allowed acceleration is real and stable, then symmetric fairy tales fade, and venting must be both vigorous and imbalanced. Either way, motion edits the script that light writes. It says yes, this glow came with a push, or no, this glow was mostly a lantern. By late December the line between those answers will sharpen. With the sun farther away in the sky, the nucleus will stand out better against its own halo. With more nights in the log, tiny trends will rise above nightly jitter. If radar gets a whisper of an echo, the size and spin will stop being guesses. Pushes you cannot see will become numbers you can plot. And numbers, once they settle, have a way of turning wild stories into simple sentences you can say without flinching. Every mystery has older cousins. Before 3i Atlas, 2 interstellar travelers rewrote our expectations in opposite directions. Oumuamua arrived first and refused to play by comet rules. It showed a gentle but real acceleration that did not line up with clear gas jets, and no obvious coma appeared even under deep imaging. That forced a round of models that tried to reconcile motion without visible mass loss, radiation pressure on a light, fractal surface, exotic ices that sublimate invisibly. None of those ideas won, outright, but the debate hardened our instincts for how to test an outlier without declaring victory too soon. Then Borisov arrived and behaved like a textbook comet from a different neighborhood. It carried a clear coma and tail, it fragmented in ways that felt familiar. Spectra matched molecules we already knew. The lesson there was humility. Not every interstellar object comes as a shock. Sometimes the universe sends a control case to calibrate our nerves. Between Oumuamua's odd push without glow and Borisov's honest glow with push sits the space where 3i Atlas now lives. What did those two teach us that matters tonight? First, speed kills complacency. Oumuamua passed quickly, and the dataset never grew large enough to settle arguments. That pushed the community to design faster response plans, so that when Borisov appeared, the machinery for rapid spectroscopy and imaging was ready. 3i Atlas benefits directly from that muscle. It means December does not begin at zero. It begins with instruments already queued and analysis pipelines already sharpened by 2 very different precedents. Second, behavior is a spectrum, not a switch. Oumuamua showed that non-gravitational acceleration does not guarantee visible gas. Borisov showed that bright comae and measurable thrust can march together in step. 3i Atlas could trace a third curve through that space, bright and possibly emission-heavy while the orbit stays nearly gravity-only. If that holds, it stretches the map rather than tearing it. A taxonomy that once had 2 bins now grows a third and maybe a fourth, and survey teams can plan for each. Third, language matters. Oumuamua's press cycle taught everyone how quickly a careful anomaly becomes an alien headline. Borisov's cycle taught the opposite risk, where familiar behavior lulled audiences into missing the quiet triumph of watching an interstellar comet behave like one of ours. 3i Atlas will tempt both mistakes. The fix is to state what the light and motion actually show and to name exactly which tests will change minds. Oumuamua and Borisov made that discipline part of the culture. We keep it now by writing predictions before the data arrive. There are technical carryovers too. The retrieval codes built to pull gas abundances from Borisov spectra can be turned on 3i Atlas with minimal surgery. The dynamical tools that tried to model Oumuamua's faint push can set clean limits on any shove from 3i Atlas. The image processing tricks used to separate a tiny core from a bright glow near the sun have grown up since both earlier visitors. This is what progress looks like in practice. We are not guessing from scratch. We are reusing tools forged in opposite fires. Most of all, the pair taught a habit of mind. Treat weirdness as a teacher, not a threat. If December says, 3i Atlas is a gas-rich emitter with blue lines stacked high and a path that barely budges, we will fold that into the family portrait without drama. If it fades like a spent spark and leaves little behind, we will file that too. The way Borisov's fragments and Oumuamua's silence both became data rather than disappointments. The point is not to force a single story to carry all our hopes. The point is to let each visitor add one line to the script of how interstellar objects behave. So the past few years were not a prelude in name only. They were rehearsal. Oumuamua trained us to live with ambiguity, while keeping measurements honest. Borisov trained us to celebrate familiar physics done in a new context. 3i Atlas now asks whether we can do both at once, because the light says unusual while the motion, so far, whispers ordinary. If we listen with the patience those two taught us, this third voice will not confuse us. It will complete the chord. Every night, the sky writes a billion little changes. Most are ordinary, a few are not. The difference is buried in pixels, and that is where machines thrive. Modern surveys subtract tonight's image from last week's and ask an algorithm to score what is new. A supernova, an asteroid, a camera glitch, a cloud edge, a cosmic ray. The model ranks them by strangeness and pushes the oddest few to human eyes. That workflow is why a story like 3i Atlas can move fast. It is also why it can go wrong if we forget what the machines are good at and what they are not. Start with training. Algorithms learn from examples. Feed them thousands of ordinary comets, and they learn what ordinary looks like. They expect a gentle rise in brightness as distance falls. They expect colors that lean neutral or slightly red. When a target turns sharply blue near the sun and brightens with a slope that looks more like a cliff than a hill, the model throws a high anomaly score. That score does not explain, it points. Humans then triage the list. Does the source move as a comet should? Do multiple frames show coherent behavior? Do. Independent instruments agree. Machines flag. People decide. Near the sun, the job gets harder. Coronagraph images carry structured backgrounds that evolve slowly. The sun breathes. Streamers shift. Detector scars pretend to be features. Modern pipelines use deep learning to model that living background and remove it, frame by frame. They learn the texture of the corona, the way noise cancelling learns the hum of an airplane. What remains after subtraction is a short list of moving points and short arcs. False alarms still happen. What kills most of them is time. A real object returns in the next frame where the orbit says it should. A ghost does not. Speed matters because signals fade. Oumuamua taught us that a rare visitor can outrun our ability to schedule big telescopes. Since then, survey networks have built real-time alert streams that anyone can subscribe to. When a pipeline assigns a high anomaly score to a moving source, the alert pings subscribers around the world. Small, telescopes can respond within minutes and grab enough frames to confirm motion and brightness trends. Larger facilities can accept a fast target of opportunity and gather spectra before the window closes. This is the nervous system that will carry December's decisions. It is already awake. Machines also protect us from our own hopes. Confirmation bias loves a rumor. If you think the comet is blue, you will see blue in a noisy image. Color extraction done by code that does not know the rumor will either find the ratio or it will not. Polarization measured by an automated reducer will either show the pattern or it will not. Photometry that runs on a fixed aperture grid will either yield the steep slope or it will flatten into an ordinary curve. By insisting on blind processing before human interpretation, teams force the data to speak in the same voice across instruments. There are limits, and they are important. Neural networks are great at recognizing what they have seen. They are less great at grading what they have never seen. An interstellar visitor that behaves unlike the training set can confuse the classifier. That is why anomaly scores exist. They are a flag that says this does not fit any box you gave me. Treating that flag as a discovery would be a mistake. Treating it as a reason to investigate is exactly right. the best systems now close the loop. When analysts confirm that a weird light curve is real, the new sequence enters the training archive. The next time a similar pattern appears, the model is less surprised, and the false positive rate falls. When analysts show that a blue tilt was an artifact born of vignetting and bad flats, that too becomes training. The model learns to discount that pattern. Over months and years, the pipeline becomes less credulous and more helpful. It begins to act like a colleague who remembers every success and every mistake. For 3i Atlas, this means 2 concrete wins. First, high-cadence coronagraph movies can be scanned for the telltale rise and color drift with a consistency no human can maintain through thousands of frames. If the pattern repeats, the score climbs, and instruments downstream can prioritize the target on nights when time is scarce. Second, ground-based follow-up can share identical reducers so that a light curve from one hemisphere and a curve from the other land on the same scale without hidden bias. That is how small scopes contribute big truth. There is a future worth naming. As the Rubin Observatory begins wide surveys, nightly data will swell by orders of magnitude. Humans will see almost nothing first. Machines will. They will not replace judgment. They will focus it. They will hand us a short list that is short for the right reasons. They will say this target is bright, blue, and moving in a way that deserves a spectrograph tonight, not next week. They will say this other target is noise, even if your heart wants it to be news. So, when we promise to follow the evidence in December, know that a quiet army of models will stand between raw photons and the charts we show you. Their job is not drama. Their job is discipline at machine speed. They will miss some things. They will overreact to others. We will correct them, and they will correct us. Together, we will turn a flood of pixels into a few honest sentences about what 3i Atlas is doing and what that means. Machines notice before we do. Wisdom is choosing what to do with what they noticed. Imagine a small spacecraft sleeping on the shelf, fueled, tested, and waiting for a name. A detector flags a strange interstellar object. A launch window opens. The clock starts. What would you send? How fast could you get there? And what truth could you bring back that no telescope can give? The dream is not a billion-dollar juggernaut. It is an agile interceptor that trades luxury for speed and answers. Start with the payload that earns its seat. You want a visible and infrared, the spectrometer to read molecules directly in the coma and on any exposed surface. You want a high dynamic range camera that can stare into a dense glow without washing out and still resolve the inner structure near the nucleus. A dust analyzer that tastes particles and weighs their composition as grains smack into it at thousands of meters per second turns brightness into chemistry. A simple magnetometer and plasma package tell you whether the solar wind is sculpting the envelope or just brushing past. None of these instruments is exotic. They are off-the-shelf ideas made compact and sturdy. The bus that carries them must be light, power-thrifty, and patient. Solar panels near the sun give plenty of power, so batteries can be modest. A medium-gain antenna can ship data daily if the target is not too far. Propulsion is a choice between a nimble chemical kick for the first sprint and steady electric thrust that slowly bends the path into an intercept. The right answer depends on discovery timing. If you know months in advance, electric wins on efficiency. If discovery comes late, a chemical stage buys you the one hard burn that matters. Navigation is the art that makes the science possible. Small bodies move fast, and their predicted positions carry uncertainties that shrink only as more observations roll in. An interceptor needs a camera that can pivot from bright stars to a faint moving target and update the aim in flight. Optical navigation does that by comparing the field against catalogs and then nudging the trajectory with tiny burns. A closing speed of many kilometers per second leaves little room for do-overs. Autonomy is not a luxury. It is how you hit a moving door before it closes. What does a flyby buy that remote sensing cannot? Range strips away confusion. Spectra taken from a few hundred kilometers do not have to fight sky backgrounds. They can separate the inner coma from the outer envelope in a single pass. Images can resolve jets, cliffs, and fractures at meter scale. A dust analyzer can measure grain sizes and composition directly rather than inferring them from light curves and polarization. Even a brief crossing can turn guesses about supervolatiles, plasma, or coatings into numbers that close arguments forever. Cost is where this stops sounding like science fiction. A small bus with a handful of proven instruments can ride a commercial rocket as a secondary payload. If you keep mass low and power simple, the bill lands in the tens to low hundreds of millions, not in the billions. Agencies already run programs that buy quick, focused missions when opportunity knocks. The missing piece is not technology, it is readiness. A spacecraft in a box cannot launch if the line item to keep it warm and staffed does not exist. Risk is honest and manageable. The target could fade, the window could shift, the flyby could miss by more than planned. You buy down those risks with a small constellation approach. Keep 2 or 3, near Earth in parking orbits, or even on shelves, ready to mate with a booster. When the alert comes, you pick the one with the best geometry and push go. The others wait for the next visitor. Redundancy spreads cost and multiplies chances of success without asking anyone to roll the dice on a single shot. There is a cultural payoff too. A standing interceptor changes how we talk about anomalies. Instead of arguing for months on social media, we plan a pass, gather the close data, and publish. The debate moves from speculation to photographs, from indirect curves to direct samples. It turns a rare event into a laboratory you can visit, rather than a rumor you can only watch. Even when we miss a given target, the existence of such a mission pressures us to write cleaner predictions and to define in advance what measurements would settle each claim. 3i Atlas is almost certainly too soon for an interceptor that does not yet exist, but it is exactly the case study that writes the requirements. What lines do we need to resolve at close range? What dust densities can our sensors survive? What closing speeds can our cameras handle without smearing the inner coma into a streak? Answer those now, and the next interstellar object will not just glide past our instruments at arm's length. It will meet a small machine built to ask better questions, up close, in the only language that never needs an asterisk. The hardest part of a live investigation is not the math. It is the language. When a signal looks wild and the world is watching, every word becomes a lever that can move public trust up or down. Say too little and curiosity dries up. Say too much and you feed a headline that outruns the evidence. The way through is a simple promise we can keep together. Tell people what we know. Tell them what we do not know. Tell them exactly what measurement could change the answer. Then, keep score in the open when the sky delivers. Start with the difference between data and story. Data are counts, ratios, line strengths, positions on a grid of stars. Stories are the bridges we build so data can cross into human understanding. Bridges must flex, but they cannot float. When we say bluer than the sun, we tie it to the ratio that made the sentence possible. When we say brightness surged, we point to the slope and the window where it steepened. When we say no strong shove yet, we link that to residuals that land within honest error bars. Every claim has a handle you can grab and test. Credit is not a courtesy, it is part of the physics. Instruments carry scars and virtues that only their teams know. When a coronagraph survives decades of duty and still pulls a moving point from the sun's halo, that is a skill earned through endless calibration. When a small telescope army stacks 5-second exposures at dawn and pinpoints a faint rise, that is craft. Citing the people and the pipelines that produce the numbers is how we keep the chain of custody clear. It tells the audience why a result is sturdy and whose past work made it so. Uncertainty deserves plain speech. We do not hide behind jargon when the question is simple. Could vignetting tilt the color? Yes, and here is the check that would catch it. Could saturation inflate brightness? Yes, and here is how shorter exposures fix that. Could gas emission dominate without much thrust? Yes, and here is what spectra and polarization should show if that is true. By naming risks and remedies in public, we turn doubt from a shadow into a to-do list. The audience learns to root for specific tests rather than for a favorite plot twist. Hype is easy to ignite and hard to extinguish. The cure is rhythm. Regular updates that carry numbers and not just adjectives steal oxygen from speculation. Small charts that show a curve creeping or flattening teach patience better than a dramatic script ever will. A simple checklist pinned to the top of a page can say what would force an update. Strong, violet lines appear, polarization maps flatten, orbital residuals grow beyond a stated threshold. Each box tells the audience exactly how a headline will change and why. Rival ideas do not need to shout. They need to write wagers. The chemistry camp can say the blue should come with diatomic carbon, as strong as a certain fraction of the continuum, and carbon dioxide that clears a certain flaw in the infrared. The plasma camp can say brightness should track solar wind speed to within a certain lag. The engineered thought experiment can say narrow features should refuse to drift with temperature and density. When those wagers sit in the light, the viewer becomes a player who knows the rules and the stakes. Open data is the habit that keeps tempers cool. When raw frames, reductions, and code are shared quickly with clear notes, replication happens fast. Mistakes are caught early and become footnotes, not feuds. If a curve softens after a reprocessing pass, we say so and show the before and after. If a color map tightens when a better flat field arrives, we say so and thank the person who fixed it. That tone invites more eyes, not fewer, and more eyes are how truth outruns rumor. Audience trust grows when we let them see the gears. We can walk through a reduction once on camera, from a noisy frame to a clean measurement, so viewers grasp why a ratio is more robust than a raw count. We can show how a position fit rejects outliers, and how the residual plot looks when a subtle thrust enters the model. We can do this without drowning anyone in symbols. The goal is not to recruit everyone into the lab. It is to raise the floor of understanding so that nonsense cannot find easy purchase. The last piece is grace. We will be wrong on details along the way, so will others. What matters is the speed and honesty of the correction. This investigation is not a sport where teams score points. It is a relay where each handoff must be clean or the baton drops. If we keep the pace, steady, give credit, admit uncertainty, publish tests, and correct in public, then whatever 3i Atlas turns out to be, the audience will remember not just the answer. They will remember how a community earned it. Every strange visitor redraws the map. If 3i Atlas holds its blue glow, or even if it folds into a brief flare, the field must update how it names and how it hunts. Old bins that split rocks from comets are no longer enough. We need categories that admit mixed behavior without forcing a false choice. Natural interstellar comets that act like locals. Natural travelers with extreme chemistry that push color and brightness to places we rarely see. Plasma-driven emitters that light up near the sun with little thrust. And a quarantine bin for true unknowns that deserve extra tests before they earn any label at all. Taxonomy is not vocabulary for its own sake. It guides budgets, software, and where telescopes look first. Surveys are the first lever, the Vera Rubin. Observatory will flood us with nightly motion tracks across the whole southern sky. Its pipelines will need fast branches tuned for interstellar kinematics, because visitors arrive with higher speeds and stranger angles. That means classifiers that flag trajectories with excess hyperbolic energy and hand them to human follow-up within minutes, not days. It also means color processing that treats blue and violet carefully, since a strong, short wavelength signal can be either a gift or a trap near the Sunday. Training sets must include synthetic cases that mimic what 3i Atlas appears to have done, so the next blue surge is recognized without panic and without dismissal. Near-sun coverage needs its own upgrade. Coronagraphs built for space weather became unlikely heroes. We can acknowledge that by flying more of them with overlapping fields and different filters, a modest constellation at key vantage points would close the blind spot at solar conjunction and give clean parallax for objects that skim the limb. Small satellites with wide coronagraphs and reliable color response are not luxury items. They're how you keep daylight from ending the story, just when it turns interesting. Cross-calibration between platforms becomes policy rather than an after-hours favor. Rapid response culture moves from aspiration to rule. Time allocation committees can reserve a small slice of nights and orbits for interstellar targets of opportunity with pre-agreed triggers. The trigger is not a headline, it is a checklist. Hyperbolic motion confirmed. Brightness rising faster than a stated slope. Color ratio beyond a stated threshold for more than a stated number of frames across at least 2 instruments. Hit the checklist, and a spectrum or a polarization sequence fires within a day. Miss it, and the target falls back into the ordinary queue. That keeps drama out and keeps fairness in. Laboratories have work to do as well. If December spectra confirm that unusual gas mixes can drive blue light at scale, we need fresh measurements of fluorescence yields and collision rates under near-sun conditions. If tiny grains seem to matter, we need better optical constants for exotic organics and for carbon-rich dust at short wavelengths. Those numbers feed the models that turn a line height or a polarization curve into production rates and grain sizes. Without them, theory hand waves where it should calculate. Education and outreach change shape too. Instead of framing interstellar visitors as a rare spectacle you glimpse and forget, We can teach them as a class of natural experiments. Each one tests a different corner of small body physics under conditions we did not choose and cannot repeat. A simple graphic that places Oumuamua, Borisov, and 3i Atlas on a triangle whose corners are glow, push, and color would let any viewer track where the next visitor lands. Add a timeline of when spectra arrive, when polarization maps lock in, when astrometry limits tighten, and the audience learns to expect clarity on a schedule rather than magic on demand. Ethics and credit must ride alongside the technical changes. Open data during the crucial weeks should be normal when safety and mission rules allow it. Shared reduction code with version locks prevents unintentional forks where one team measures blue and another measures neutral because a filter curve differed by a few percent. Credit lines that list instrument teams, amateur networks, and analysis groups on the same slide remind everyone that discovery is a chain, not a crown. Finally, mission plans shift from someday to soon. A standing small interceptor program becomes a line item rather than a white paper. The first pair might miss the perfect target, and that is fine. The point is to have boxes you can open when the next curve steepens toward impossible. You do not build a fire station after smoke rises. You build it because you live in a forest, and you know wind and chance will eventually line up. If 3i Atlas ends up as a natural object behaving at the edge of what we have modeled, the map grows and our tools sharpen. If it fades into calibration, the map still grows, because we learn exactly how instruments can fool us, and we insulate the next hunt against the same mistake. Either way, we leave this season with clearer categories, smarter surveys, steadier procedures, and a public that understands why patience is not hesitation. It is the speed at which truth travels when you clear the road. Picture the first safe evening after sunset. The sky cools from gold to deep blue. The sun is well below the horizon, and the glare has relaxed. This is your window. 3i Atlas sits low at first and climbs a little higher each day. The exact spot depends on date and latitude, so lean on trusted ephemerides in your favorite astronomy app and cross-check with reputable observatories. You are not hunting a sparkling star. You are looking for a soft blur that moves a tiny step from night to night. If the bright future wins, the blur will be obvious in binoculars. If the fading future wins, you will want a small telescope and patience. Safety comes first. Never push optics anywhere near the Sunday. If the separation is small on a given date, stand down and wait. Use a sturdy tripod, balanced mount, and gentle motions. Let equipment cool, so focus holds steady. Choose a site with a clear horizon and low twilight glow. Turn off white screens and bright headlamps. Red light preserves night vision and makes you a better observer within minutes. What you may see depends on which road the story takes. In a sustained glow, the coma will look plump and evenly lit with a hint of blue in long camera exposures. A tail may appear faint at first, then lengthen as geometry improves. In a fast fade, the coma will shrink and soften. The object may look like a pale knot that resists casual viewing. Do not be discouraged. Subtle targets are where technique matters and where your notes help the community most. For cameras, short exposures stacked are safer than long single shots. Try many frames between 1 and 5 seconds to protect stars from smearing and to dodge tracking errors. Stack them with alignment on the comet to let the faint coma rise from the background. Calibrate with dark frames and flats if your software supports them. Keep a simple log that notes start and end times, location, telescope, and lens details, and the number of frames used. Timestamps in local time plus offset or in universal time are both fine as long as you are consistent. For visual brightness estimates, compare the comet to nearby stars of known magnitude and bracket the value with a brighter and a fainter star. Defocus slightly to spread the light and make the comparison easier. Write what you judged and why. If you repeat the estimate an hour later and get the same answer, confidence grows. If you and a friend in another city agree within 1/10 of a magnitude, confidence grows again. Color is harder, but not out of reach. Many consumer cameras record enough blue and red channel information to hint at a tilt. Take match stacks through a blue filter and a red filter if you have them. Keep exposure times and processing steps the same. If the blue stack consistently shows a higher signal in the coma region than the red stack, note it carefully and share the raw data along with your method. Professionals can judge the quality and fold it into larger maps. Reporting turns a private night into public science. Established networks and comet sections exist precisely to catch these windows. They standardize formats and check consistency so that one person's good night can stand beside another's. If you are new, team up with a local club or an online group that has submitted observations before. Let them mentor your first report. You will learn the small habits that turn enthusiasm into usable numbers, temper expectations, and to enjoy the craft. Some nights, clouds win. On other nights, the target sits in bright twilight and refuses to pop. Keep your routine anyway. Even a non-detection with honest limits helps contour the light curve. If you do catch a change, be conservative with language. Show the sequence. Show the numbers. Let others reproduce the result before you add adjectives. That tone helps the whole story keep its balance. A simple checklist can focus each session. Confirm safe separation from the Sunday. Confirm the latest coordinates. Capture a short stack for motion. Capture a longer stack for the coma. Try one filtered sequence if the target is bright enough. Make one visual brightness estimate. Log everything with times and settings. Share through a channel that archives and credits contributors. Then step back and look up, without gear for a minute. You are watching a messenger from another star system write a line across our sky, and that is worth a breath. If you want to support the larger investigation beyond observing, share the measured facts with friends who are curious. Point them to the 3 questions that decide December. Did the color stay blue? Did lines rise in spectra? Did the path show a shove? That framing turns a conversation into a shared watch. It keeps wonder warm and hype cool, and it makes the next clear night feel less like a chase and more like a rehearsal for truth. Stand at the edge of what we know and look back for a moment. A traveler from another star raced past the sun and for a handful of hours wrote blue light into our instruments. We argued. We built checklists. We promised to let spectra, polarization, and motion call the winner. In a few more clear nights, we will have the pieces to assemble a single sentence that does not flinch. Either a volatile-rich comet lit its own halo under brutal sunlight, or plasma turned a vast gas cloud into a lantern, or the signal dissolved under calibration, or a stranger possibility survived every ordinary test. That is the full menu. No romance wasted, no rigor spared. Here is what that single sentence will rest on. Lines or no lines. If cyanogen, diatomic carbon, oxygen, carbon dioxide, and carbon monoxide stand tall and consistent, chemistry is the spine. If the spectrum is line-rich and time-linked to the solar wind, plasma is the spine. If lines fade, the color returns to neutral, and polarization climbs with a dust phase curve. Reflection takes the stage. If the light remains narrow and stubborn while nothing in the catalogues matches, the field turns as one toward replication that does not blink. That decision tree is not poetry. It is the roadmap we drew together. Motion will close the last door, a measurable shove that grows with brightness and leans away from the sun, says powerful vents. A quiet path with a loud glow says emission, not expulsion. Radar, if we get even a whisper, will tell us whether the core is a compact shard or a fluffy snowball. None of this needs a leap. It needs patience, plotted in hours and days instead of months and years. The universe handed us a fast mystery that fits human attention spans for once. We can meet it in real time without losing our standards. What changes if the answer is natural? More than you think. We will have watched an interstellar body ride the near-sun furnace and behave at the edge of our models. That stretches comet physics, refines volatile budgets, and forces laboratories to measure optical constants and fluorescence yields under conditions they rarely attempt. The next blue-tinged visitor will not surprise us. We will have training data where there was only rumor. We will have a taxonomy that admits uncommon does not mean unbelievable. What if the answer is artifact? That too is progress. We will write down exactly how coronagraphs can conspire to fake a color and a curve across different platforms. We will update pipelines, swap flats, and lock versions so the same mistake cannot live twice. The next near-sun excitement will get sorted in hours rather than weeks. Confidence in real anomalies becomes stronger when we are fluent in beautiful mistakes. And what if something stranger survives the gauntlet? Then the same culture that protected us from wishful thinking will protect the evidence from us. The tests will repeat at new wavelengths and on new nights. Instruments with different scars will see the same shapes. Teams that disagree on everything else will agree on the numbers. The conclusion will arrive not as a shout, but as a weight, the kind that settles on a table when many hands let go at once. Either way, you were not just a spectator. You learned how colour is measured, why ratios beat adjectives, how small pushes are read in tiny drifts, why polarization twists light into a truth about dust, and how a community can argue hard without breaking. You saw how amateurs shoulder nights that big mirrors cannot fill, how engineers teach detectors to behave, how skepticism and wonder can share a bench without sliding into cynicism or hype. That is the real long tail of a live investigation. The answer matters. The method endures. When the final plots land, we will read them together. We will say out loud which wagers won and which we fold. We will thank the quiet instruments that stared into glare and the patient eyes that tracked a faint blur at dawn. Then we will archive everything against the day another visitor writes a new colour into the sky. That is the promise we began with and the one we keep now. Follow the evidence, credit the craft, change your mind in public when the sky earns it. The glow was the hook. The answer is the inheritance.